In this lesson, we'll be looking at systems of nonlinear equations. Solve the system of equations by graphing each function and finding where the two intersect. So we'll first graph the square root of x. We have 0, 0, 1, 1, 4, 2, and we'll play connect the dots. Hopefully this is a familiar function that we've seen in the past. And then we'll have the line y equals 6 minus x. First we have a y-intercept at 6, and our slope is -1. So we'll go down 1, right 1, and continue that pattern all the way down. Play connect the dots, and we have the graph of our line. And we're looking for where they intersect. They intersect at the point 4, 2. So the solution to this system is 4, 2, where the two intersect. Now we're going to do the same thing using algebra and substitution. Remember, when we substitute, we're going to take one of the equations and substitute it into the other. So I'm going to replace the y in the second equation with the square root of x. So we have the square root of x equals 6 minus x. And now we just need to solve this. To solve this, we need to first square both sides. And now we have a quadratic. With this quadratic, we will set it equal to 0. So we'll subtract x over, and I'm going to reorder these terms to make it look better. So we have our quadratic. Next we'll factor this. We want two numbers whose product is 36 and whose sum is -13. That is -4 and -9. Set each factor equal to 0. And we get x is 4 and x is 9. Now that should raise an alarm. If we're getting two different x values here, that's an indication that there's two solutions. But our graph indicated that there's really only one point where the two curves intersect each other. So this is a good time to point out sometimes you can get extraneous solutions. So it's going to be important to check our answers when we're using algebra, because in this case you can sometimes get extraneous solutions. So let's test 4. Let's see if 4 is correct. When we plug in 4, y equals the square root of 4, which is 2. And now let's also plug in 4 for the second equation. We get 2 in each case. So that seems like that's a good thing. We get 4, plugged in 4, and it spit out 2. So it looks like that is good, which confirms our previous answer. Let's also check the 9. So we're going to plug in our 9 into the x. Y equals the square root of 9, which we know to be 3. Y equals 6 minus 9, which is -3. Here, the answers do not agree. Our y variable is different in each case, so that means 9 is an extraneous solution. So 4, 2 is our only coordinate that is true, and that confirms our graph. The methods of solving systems of nonlinear equations mirrors the methods used to solve systems of linear equations: graphing, substitution, and elimination. However, we cannot use matrices for nonlinear systems. Matrices only work when you have linear equations. So let's use substitution to solve this system of nonlinear equations. I'm going to take this expression and replace the y in the second equation. We have x squared plus 1 minus 4x equals 1. Notice we're just replacing this y with x squared plus 1. And now we need to solve. This looks like a quadratic, so I'm going to subtract the 1 over. X squared minus 4x equals 0. And from here we can factor. Pull out the GCF. And we get x equals 0. X minus 4 equals 0. So x is 0 and x is 4. So it looks like we have 2 points of intersection for now. Let's plug in our x's to see what y is. 0. Let's see what we get. 0 squared is 1. Let's check in the other one as well. Y minus 4 times 0 equals 1. And that means y has to be 1 here as well. So it looks like when we plug in 0, both equations give us a 1. So since they agree, we know that 0, 1 is a point where those two intersect. Now let's check the 4. So we need to do the same thing. We need to plug in 4 for both equations. 4 squared is 16 plus 1 is 17. And then on the second one, 4 times, replace x with 4. Set that equal to 1. Y minus 16 equals 1. Add 16 to both sides, and y equals 17. So in this case, we got 17 for the top and bottom equation. That means 4, 17 is a point where the two graphs intersect. So it looks like the graphs are intersecting in 2 locations. Let's see if that's true when we graph it. Now we'll solve this using graphing. Our first equation is just a quadratic that has been shifted up 1 unit. So we'll plot those familiar points, 0, 1, 1, 2. Then it would normally be 2, 4, but we're going up 1, so that'll be 2, 5. 3 squared is 9, plus 1 is 10. 4 squared is 16, plus 1 is 17. And we'll just mirror that on the left side. Play connect the dots. And we've got our quadratic. The next equation, the bottom, we need to add 4x to both sides to get y by itself. So we have a simple linear equation. Y-intercept is at 1, and then our slope is 4, so we go up 1, 2, 3, 4, right 1, and repeat that pattern. Up 1, 2, 3, 4, right 1, and we'll just continue that pattern. Play connect the dots. And we can see that the curves are intersecting in 2 different locations. At 0, 1, and again at 4, 17. And if we go back to the previous example, notice 0, 1 and 4, 17. Our algebra confirms our graph. They're the same. Next, let's solve this system using elimination. Remember, with elimination, we want to add the 2 equations so that one of the variables disappears. If we add right away, notice nothing's going to disappear. If we multiply the bottom equation by -1, we'll get negative x squared plus y equals 7. We'll leave the top equation as it is. And now notice that when we add these 2 equations, the x's cancel. You're left with y squared plus y equals 20. From here, we have a quadratic, so let's set it equal to 0. Y squared plus y minus 20 equals 0. Factor. Y plus 5, y minus 4. equals 0. Set each of those equal to 0. And we get y is equal to -5 and y is equal to +4. Let's check. So we're going to check -5 first. So this time, notice y is -5. So we're going to replace the y's with -5. I'll do it to the top equation first. We're getting x squared plus 25 is equal to 13. Subtract 25 on both sides. And we get x squared is equal to -12. And now when we take the square root of both sides, we're getting plus or minus the square root of -12, which is an imaginary number, which means that can't happen. So that point we're going to ignore. It's not part of the solution. It can't be there because we're getting imaginary numbers. We'll do the same thing. Let's test y equals 4. And again, we can use the top or the bottom equation to begin with. It doesn't matter. So x squared plus 4 squared, replacing the y with 4, equals 13. X squared plus 16 equals 13. Subtract 16 on both sides, we get x squared equals -3. And square root of both sides, we get the square root of -3, which again is an imaginary number. So if both of these are saying we get imaginary numbers when we plug in both -5 and 4, it looks like there is no solution to this system. Those imaginary numbers mean that those two curves are not intersecting. If they're not intersecting, there must be no solution to this system. Let's prove that with a graph. So if we look at this graph, x squared plus y squared equals 13. Remember from chapter 2, this is a circle centered at the origin with a radius of the square root of 13. The square root of 13 is roughly 3.6, so roughly 3.5. So we're centered at the origin. Radius is roughly 3.5. So we'll go 3.5 in every direction, play connect the dots. And just pretend this is a circle. I know it's a horrible drawing, but the grid is off scale. So here we have a circle centered at the origin. Radius is roughly 3.5. Next we have x squared minus y equals -7. If it helps you, let's rewrite that so that y is by itself and it'll be more easily recognized. So -y is equal to -x squared minus 7. Divide by -1 and we get x squared plus 7. So that's your basic quadratic that has been shifted up 7 units. So the vertex is at 7 and it's going up. Notice those two curves never intersect each other. Therefore, the solution to this system is no solution. They never intersect, therefore there's no solution. Next, we'll look at this system, and it's saying solve using any method. So our options, again, are we can graph it, we can substitute, or we can use elimination. Matrices do not work since these are nonlinear systems. And it looks like elimination is not going to work here. There's no way for me to add these two and make something cancel. So we have to use substitution. So with substitution, you want to isolate one of the letters in one of the equations. The easiest thing to do is going to be using the bottom equation, and we can isolate the x or the y. It doesn't matter which. I'm going to choose to isolate the y and say y is equal to 3 divided by x. So I'm simply isolating the y by dividing x on both sides. And we're going to take this value and plug it into the other equation, the top one. So now we're going to replace y with 3 over x. So I have x squared plus y squared equals 10, the first equation, and we're going to replace y with 3 over x. Now we just need to go through and simplify this. Here we have x squared plus 3 squared is 9. X times x is x squared. That's equal to 10. And notice we have a fraction here. We want to eliminate that fraction, so we're going to multiply every term by the LCD, which is x squared. Get rid of that fraction. We get x to the 4th plus 9 equals 10x squared. From here, we'll set it equal to 0 by subtracting 10x squared. So x to the 4th minus 10x squared plus 9 is equal to 0. At this point, hopefully this looks similar to something you've seen in the past. It's been a while since we've done this, but notice we're going to need to use a u substitution here. We're going to let u be x squared. So we now have u squared minus 10u plus 9 equals 0. Now we have a quadratic that we can factor. U minus 9 times u minus 1 is equal to 0. U minus 9 equals 0, and u minus 1 equals 0. So I'm just going to copy that up here. Remember, we don't want u's. We want to replace those u's eventually. Once we solve for u, we're going to go back in and replace those u's with x squared. So x squared equals 9, and x squared is equal to 1. Take the square root of both sides, and we get x equals plus or minus 3, and x is equal to plus or minus 1. So it looks like we have 4 points of intersection right now. Let's figure out what y is. Remember, this is only part of our solution. We need to figure out what the corresponding y values are. So we're going to take each of these x values and plug them into the y equation. So when x is negative 3, y is 3 over negative 3, which is negative 1, meaning our coordinate is negative 3, negative 1. When x is positive 3, y is 3 over 3, which is 1. So our coordinate is 3, 1. And when x is negative 1, y is 3 over negative 1, which is negative 3. So we get negative 1, negative 3. And when x is positive 1, y is 3 over 1, which is 3. So we get 1, 3. So we have 4 solutions here. And keep in mind, you should go in and check these. You can graph it to check. You can also plug in these numbers to the 2 equations to see if they work. And they will. This one has 4 points of intersection.